Good morning students. In the previous two video lectures, we have discussed about the data transfer instruction, arithmetic instruction and logical instruction. In our today's video lecture, we will be discussing about the branch instructions available in 8085 microprocessor. Branch instruction. The branch group instruction allows the microprocessor to change the sequence of program either conditionally or under certain test condition. The group includes jump instruction, call and return instruction, restart instruction. The first branch instruction what we are going to see is jump. The jump instruction is denoted by means of JUMP followed by means of a 16-bit address. The jump is unconditional to the address. The instruction loads the program counter with the address given within the instruction and resumes the program execution from specified location. For example, if you give jump 2000 and you assume that this jump instruction is in the address location 5100. So what the program counter will do? The program counter will be pointing out this particular instruction only. We know the functionality of program counter is nothing but to hold the address that should to hold the address of the instruction that should be fetched next. So it is pointing towards the address location 5100 and 5100 is nothing but of a address of this jump instruction. So once this instruction is being executed, what happens is that the program counter is being loaded with this 16-bit address which is followed by means of the jump instruction. So the program counter will fold 2000. Once the program counter folds 2000, what the microprocessor will do? It will jump, it is going to branch or it is going to jump to the address location 2000. Initially, before execution, it was in the address location 5100. After the execution of this JMP followed by means of a 16-bit address, it is going to jump to a specified address location called 2000. If it is of JMP 3000 or JMP 6000 means what it is going to do after execution, the program counter is going to hold 6000 and the microprocessor will jump from 5100 to 6000. Next we are going to discuss about conditional instruction. Why we call this instructions as conditional instruction is based upon some conditions this particular instruction is going to branch or it is going to jump to the user specified address location. In the previous slide we have discussed about the unconditional jump instruction, that is that particular instruction jumped to a specified address location without any condition, so we called it as unconditional. Here the instructions are going to jump to a specified address location with some conditions if some conditions are satisfied, right? The first conditional instruction what we are going to see is JC stands for jump on carry followed by means of a 16-bit address. What it will do is it will check that once this instruction is being executed, what the microprocessor will do is the microprocessor will first check the carry flag bit in the flag register. If that carry flag bit is being set, then the instruction will jump to the user specified 16-bit address location. If carry is being set in the flag register, then jump to the user specified address location. That is what the meaning for this jump on carry. Next is JNC followed by means of 16-bit address. So what this instruction will do is if carry is not setted in the flag register at that instant of time, you jump to the 16-bit address location what is being specified, right? Next instruction is JP. JP stands for jump on positive. If sign flag is equal to 0, then at that instant of time, jump to the user specified 16-bit address. JM stands for jump on minus. If the sign flag is equal to 1, then it is going to state the minus, that is the accumulator signal, accumulator content is of a minus value. So at that instant of time, the instruction jumps to the 16-bit address what is being specified by means of the user. Next instruction is JPE, jump on parity even, right? If the accumulator content is having even number of ones, then at that instant of time the parity flag bit will be equal to 1. So at that instant of time, if parity bit is equal to 1, then jump to the user specified 16-bit address. JPO stands for jump on parity, odd parity, jump on odd parity to the specified 16-bit address. If parity flag bit is equal to 0, then jump to the user specified address location. Next two instructions are jump on 0 and jump on no 0. When the 0 flag is in the flag register is equal to 1, at that instant of time, jump on to this 16-bit address location what the user has specified. When 0 flag is not equal to 1, or if it is equal to 0, at that instant of time jump to the 16-bit address location. Next branch instruction is call. Call is an unconditional a subroutine whose starting address given within the instruction and used to transfer program control to a subprogram or subroutine, right? So the previous instructions what we have discussed is nothing but of jump. This jump instruction is going to jump from one location to other location within the program. If we are writing several sub programs, suppose if we are having a very big program in which some lines are being frequently used by means of the main program, then we can collect those common lines and we can write it as a subroutine and we can call it whenever we are in need. You might have written such subroutines in your C language, right? So in the same fashion, if a repeated action have to be done by means of the processor, then those repeated actions are being collectively written in a separate memory location called subprogram or subroutine, and that subprogram is being called by means of main program at the time of need, right? Suppose if you want to call that particular subroutine, we will be making use of this call instruction. Call instruction opcode is CALL followed by means of the address where the subprogram is being located, right? Let us see some conditional call instruction. Call on carry. If carry flag is set, then jump to the 16-bit address location what is being specified here. Next is of call on not carry. If no carry bit is being set, then jump on call the specified 16-bit address location. Similarly, call on positive, call on minus, call on parity even, call on parity odd, call on 0 and call on not 0. It is much similar to that of the jump instruction. In the jump instruction, the the 16-bit address what we have specified here will be within the program, that is within the main program. In the call instruction, we will be having main program as well as sub program. So whenever the microprocessor wants to call a sub program, then it will be making use of this call instruction call instruction followed by means of a 16-bit address. This 16-bit address is out of the memory of main program, right? Next instruction is return instruction, RET. So I have told that call instruction is used to call the subroutine program. Suppose after executing the subprogram, the microprocessor wants to get into the main program again. At that instant of time, the instruction what is being used for returning to main program is return, RET. So this RET instruction what it does is it returns from the subroutine unconditionally. This instruction takes return address from the stack and load the program counter with this address. That is, we can see an example. So stack pointer is holding an address of 27FD and 27FD is 00 and 27FE is of 62. Right? The 62 and 00 are nothing but of the main program's address. Right? This main program's address. Once the call instruction is being executed, at that instant of time the program counter will be holding the main program's address, right? So that main program address is being pushed inside the stack pointer, right? Then it moves to the subroutine program, and after executing the subroutine program, what it will do is it will return to the main program by means of this RET instruction. So what this RET instruction will do is it will pop or it will take out the address from which it has to reassume in the main program. I have told that before the call instruction is executed, the program counters content, the program, we know that the program counter is going to hold the address of the next instruction to be fetched by means of the microprocessor. So what it will do is after call instruction, some instruction, the user might have written some instruction, so the program counter will be holding the next instruction, next address location of the call instruction. So the next address is being pushed inside the stack pointer before the call instruction is executed. So once the call is being executed, it is going to branch to a subprogram. After completing the subprogram, it will be returning back to the main program. How it will return us, it will check the stack pointer first, right? The stack pointer is initially pointing towards the address 27FD. Once this return instruction is being executed, what it will do is it will take out the 00 and 62 out of the stack pointer and it will be loaded inside the program counter. So the program counter is now loaded with the address 6200, that is the address of, it might be the address of main program and the main program starts executing from where it has been left. Next instruction what we are going to discuss is control instruction. The first control instruction what we are going to see is no operation, NOP, right? No operation. Once this instruction is executed, no operation is being performed by means of the microprocessor. The instruction is fetched, decoded, but no operation is executed. The next control instruction what we are going to see is halt. HLT stands for halt. The CPU finishes executing the current instruction and halts any further execution. An interrupt or reset is necessary to execute from the halt state. Next instruction is read interrupt mask. This is a multi-purpose instruction used to read the status of interrupts 7.5, interrupt 6.5 and interrupt 5.5. We will discuss about this RIM instruction and SIM instruction. The next instruction what we are going to see is SIM instruction in detail while we are discussing about the interrupt structure of 8085. You just know there are two instructions called RIM and SIM instruction. This RIM instruction is used for read the interrupt mask, and the next instruction SIM. is used for setting the interrupt marks. These two interrupts are used for setting and resetting the interrupts which are all being available in our 8085 microprocessor. We have seen that there are interrupts like 7.5, 6.5, 5.5 while we are discussing about the pin diagram of 8085 microprocessor. We will be discussing about the sim and rim instruction while we are discussing in detail about the interrupt structure of 8085, right? So we have completed the 8085 instruction set. Now we can start doing some simple programs. Let us start with 8-bit addition without carry, right? I have shown a sample program over here. This is the way how we have to write the program. The first column is of address, next is label, next mnemonics, then hex code and comments, right? First we will be writing the mnemonics. After writing the mnemonics, I will tell you how to write the address, right? First, since it is of 8-bit addition, for 8-bit addition, what we are in need, we are in need of two datas. Suppose the sample input what we are going to choose here is of 02 and 0C. So we are going to add 02 and 0C, right? In order to add these two datas, we have to provide one data for any arithmetic operation or logical operation through accumulator, and another data can be from any of the register. This we know, right? And after any arithmetic or logical operation, the result will be in the accumulator only. So we have to permanently store it in the accumulator. This is the flow or algorithm for addition. So now we know that one data should be in accumulator and another data should be from a general purpose register. So we know we have discussed about the move instructions. We can make use of this move immediate A. What this move immediate A followed by means of 8-bit data will do, it will load the 8-bit data immediately into the accumulator. So one data is being loaded into the accumulator, right? Next we are in need of the second data. That second data can be loaded in any of the general purpose register. Here I have used B register. You can make use of C, D, E, H or L register, right? You can make use of the other five general purpose registers which are all being available. So what I did, I have loaded the second data 0C immediately into the B register. So now my accumulator is being loaded with 02 and B register is being loaded with 0C. So I have loaded the inputs to the accumulator and register. The next task is, after loading the input, the next task is add. We have to perform addition. So we know that the instruction for adding the number is add, right? Add followed by means of B. What this instruction will do, it will add the content of accumulator with the content of B register. It will add the content of accumulator with B register and the result is stored in accumulator, right? So after adding, the result is an accumulator. We cannot see the accumulator register, right? So we users can view only the memory. So what we have to do, we have to move the content of accumulator to a specified memory location, right? So in order to move the content of accumulator to a specified memory location, the available instruction is STA. STA stands for store the accumulator content in the specified 16-bit address location, right? So here I have specified a address location of 9100. You can give any of the address, right? So I have given here it as 9100. So what the microprocessor will do, it will store the result of the addition in the memory location 9100. So my task is completed. So what I have to do, I have to terminate the program. So the instruction for terminating or halting the program is HLT. So I have given a halt. First what I have did, I have loaded the inputs to the general purpose register and accumulator. So I have loaded, since one input should come from accumulator, I have loaded immediately the accumulator with the data 02. Next I have loaded a general purpose register. Next, after loading the data, I have added, since I know that the result of addition is an accumulator, I have to store it permanently in memory. So I have stored it permanently in memory now. After, since the task is completed, I am terminating the program, right? So how the processor will do is, it will take this 0 to 0C input, and I've told that we will be feeding only the hexa values to the processor. That hexa values are being converted to binary form, the machine language or machine code, by means of the instruction decoder. The instruction decoder duty is to convert the hexa value or hexa code, whatever we are feeding to the microprocessor, is being converted to binary form by means of the instruction decoder. So the hexa value what we have provided will be converted into binary form by means of the processor. After converting it to binary form, it the processor will perform binary addition. After performing binary addition, before giving it to the user, what it will do, it will convert the binary value to again back to the hexa value, and the hexa result will be stored in the specified user specified memory location. So if we add 0C and 02, what it will be, C is equal to what, A is equal to 10, B is equal to 11, C is equal to 13, D is equal to 14, F is equal to 15 in hexadecimal value. So we have provided 0C. So 0C is equal to what? Yes, it is equal to, so by means of adding those two datas, we'll be getting 0E, right? Now I will tell you how to write the opcode for the program what we have written. This is nothing but of the opcode sheet for 8085 microprocessor. You can download it from net. Now I will tell you how to make use of this opcode sheet to write the hexa code, right? The first instruction is move immediate followed by means of a 8-bit data. So this sheet consists of all the instructions what we have discussed. So we have to look over the used instruction in our program in the opcode sheet. The instruction what we have used is move immediate a comma 8-bit data. So we have to check over here, right? So if we check over here, it is here, move immediate a comma 8-bit data. So the mnemonics for move immediate a comma 8-bit data is nothing but of the mnemonics. The hex code for the mnemonics move immediate a comma 8-bit data is 3E. So I have written 3E, right? 3E is nothing but of mnemonics for move immediate a. What it has to immediately move, it has to move the 8-bit data. So 3E, by means of decoding 3E, processor will comes to know that it has to immediately load something, some 8-bit data into the accumulator. What data? The data is being followed by means of the hex code. So 02 is nothing but of the data. 3E is nothing but of the hex code for move immediate A, which we have obtained by means of looking over the opcode sheet. Similarly, we have to check the hex code for move immediate B comma 0C, right? The move immediate B comma 8-bit data's hex code is 06. So 06 followed by means of the given 8-bit data. Next we have to see the hex code for add B. So the hex code for add B is 80, right? So we have performed addition. Now we have to store the accumulator content to a specified address location. So now we have to search the hex code for store accumulator STA, right? So see, we can find the hex code for store accumulator 16-bit as 32. The hex code for STA is 32. So I have written here 32. Then we have to write the lower order address followed by means of higher order address. While we are discussing about the address bus, I've told that the processor will first take the lower order address. First it will read the lower order address, then only it will read the higher order address. So we have to give it in the reverse form 0091, right? Next we have to find the hex code for halt in the opcode sheet. The hex code for halt is 76. Yes, it is here. So the hex code for halt is 76. So we have to write it in such a manner. We have to write the hex code by means of looking over the opcode sheet. So first we have to write the mnemonics. After writing the mnemonics, we have to search the hexacode for the written mnemonics, and we have to fill this hexacode column. After fixing this hexacode column, we have to write the address. We can start the address in from any address location point. Here I have started my program from the address location 8000. So in 8000 is a 16-bit address. We know that a 16-bit address in 8085 microprocessor will hold only a 8-bit data. So 8000, in 8000 location 3E is being loaded, and 3E is a 8-bit data. So it is being loaded with 8000. Where we have to load the 02? The 02 is loaded in the next address location 8001. So 8001 is being occupied by 02, right? So it is a 2-byte instruction. Since it is going to occupy 2 address lines, so we will be calling it as a 2-byte, a byte. 3 is a byte, 02 is another byte. So this move immediate a comma 8-bit data is a 2-byte instruction. It occupies 2 memory location, 3 a byte in one memory location and 02 in the consecutive memory location. So 8001 is meant for 02. So the next mnemonics will start from 8002, because in 8001 02 is loaded. So the next mnemonics addresses of 8002. So in 8002 06 hex code will be there, and 0C the immediate data will be in the next address location 03, because the same move immediate is here, and just now only I have told that the move immediate is a 2-byte instruction. It is going to hold a 8-bit data in one memory location 8002 and the next 8-bit data in another memory location. So 8003 is meant for 0C data. So the next address is for the mnemonics is 8004, right? So add B is a single byte instruction. Only opcode hexacode is there. Only opcode is there. No operands are being there. Isn't it or not? So it is a single byte instruction. So in 8004 80 will be there. We can write 8005 for the next mnemonics. Here if we see the next instruction STA, so the STA has a hex code of 32 followed by means of a 16-bit address 00 and 91. So 32 is a 8-bit, again 00 the lower order address is a 8-bit, 91 is again the higher order address is a 8-bit. So this STA is a 3-byte instruction. It is going to occupy 3 address locations. So 32 will be in the 8005, in 8006 00 will be there, and in 8007 91 will be there, and in 8008 halt is located, right? So 8008 is 8005 for 32, 8006 for loading 00, 8007 for 91, and the next address is of 8008 where this 76 hex code for halt is written. This is how we will be writing the address, right? Clear with this? I have written the same program in a different manner here by means of using different instruction sets. So what I did is the same addition program without carry. First I have loaded the accumulator, right? After loading the accumulator, what I have done, I have moved the accumulator content to B register. That is, the data one is now in B register. So I'm now in need of the second data, and so for that what I am going to do is I am immediately loading the second data in accumulator. Why I am loading it in accumulator is, in order to perform any arithmetic or logical operation, one data should be from accumulator and other data must can be from any of the general purpose register. Here initially I have loaded the first data in the accumulator, but what I did, I moved it to the general purpose register. Since I have moved it to the general purpose register, I am in need of the second data that should be in the B register only. So I am going to make use of the move immediate instruction, and I can load the second data in accumulator. Since I have got two data, what I can do, I can perform addition operation. I know that the result of addition operation will be temporarily in accumulator, so I have to permanently store it in a memory location. So I am going to store it, then I am going to terminate it. We can write the same program in some other way also. That is, we can immediately move the B register with 0 2 and C register the next C register with the second data. After loading the first data in B register and second data in C register, one register data can be moved to accumulator, then we can perform addition also, right? So as we are thorough with the instruction set, we can write a program in multiple ways, right? Now I'm going to give an assignment to you. You just write this assignment in your classwork note or whatever note you are maintaining for microprocessor, and have it with you. During our online class, you can show it, and we can discuss the program what you have written. So the assignment one is, you have to write 8-bit addition with you by means of using LDA instruction. I have shown the 8-bit addition without carry by means of using the move and move immediate instruction. You try to write 8-bit addition without carry by means of using LDA instruction, and you also try to write 8-bit subtraction without borrow, right? That's all with the instruction sets of 8085. Let us have a quick summary on the instruction sets what we have discussed so far. So the first instruction set what we have discussed is of data transfer instruction. We have discussed about move followed by means of registers, two registers, source and destination register, or a source register and memory. That is, move or copying the data can be done within the registers or from register to memory. Move immediate followed by means of a 8-bit data, a register and 8-bit data. The immediate data which is being specified here will be moved to the memory or the register. Next is load accumulator, LDA. Load accumulator directly from the memory. The user will be specifying a memory after the LDA instruction along with the LDA instruction. So the memory location will be holding a data. That particular data will be loaded inside the accumulator. STA, store accumulator, followed by means of a 16-bit address. Store the accumulator content in the specified 16-bit address location. The user will be specifying a 16-bit address location. The accumulator content will be permanently stored in the specified address location. Next instruction is LHLD, load the HL register pair directly from memory. A memory address will be there. This memory address location content will be loaded in the L register, and the next consecutive memory address location will be holding a data that will be loaded in the H register. SHLD is nothing but of storing the H and L registers data directly into the address specified here. Next we have seen LXI. LXI stands for load register pair with immediate data. The next instruction what we have seen is load accumulator from address in register pair, and STAX stands for store accumulator in address in register pair. Exchange, it is going to exchange the data between HL register pair and DE register pair. XTHL stands for exchanging top of stack with HL register. Here, if you note here, in all these instruction, X is being there. What this X denotes is an X in the name of data transfer instruction implies that it deals with a register pair. So once you see the X, you have to literally, your mind have to literally think that that we are going to use the register pair, that is the microprocessor is going to use register pairs. Next we have started discussing about the arithmetic instruction. We have discussed about the add instruction, add immediate, add with carry, add immediately data to accumulator using carry, subtract from accumulator, subtract immediate data from accumulator, subtract from accumulator using borrow, subtract immediately from accumulator using borrow, increment specified by 1, decrement specified by 1, INX, X stands for register pair, increment the register pair by 1, DCX, decrement the register pair by 1, R stands for register, it is going to increment the register content, here it is going to increment the register pair. That double register add, and we have seen the logical instructions, and logic, and immediate, or logic, or immediate, XR logic, XR immediate. Also we have seen the compare instruction, CMP, compare immediate data, rotate accumulator left, rotate accumulator right, rotate accumulator left through carry, rotate accumulator right through carry, complement accumulator, complement carry flag, set the carry flag. And we have seen the jump instructions. Conditional, unconditional jumps are jump, call, and return. Conditional jumps such as jump on no zero, jump on zero, jump on no carry, jump on carry, jump on positive, jump on even parity, jump on odd parity, jump on plus, and jump on minus. Next we have seen some stack related operations such as push, pop, XTHL, exchange top of the stack, move the content of H and L to the stack pointer. Also we have seen the IO instructions in and out. And we have seen some of the machine control instruction: enable interrupt, disable interrupt, halt, no operation,